My name is Jason Baiocchi. I am an ACC student participant in the Summer Undergraduate Research Experience course here at the Petroleum Engineering Department at UT Austin. This summer, my team and I were tasked with studying the physical characteristics that affect fluid flow in rocks, particularly porosity and permeability. Now, we were given 4 different rocks to look at, 2 sandstones and a limestone, both of those from the continental United States, as well as marine sediments that we gathered from the south coast of Japan. Now, we were studying these to hopefully expand existing knowledge in this area, look for new angles to try and hopefully increase recovery and extraction rates in the petroleum industry. Now, from the outset, we expected porosity and larger median grain size and better sorting would all lead to greater yields and permeability. Now, from the outset, our porosity and permeability measurements for the Nankai samples from Japan were given to us for time constraints, but the rest we calculated ourselves. We first calculated porosity directly for the sandstone and limestone by taking the difference between their saturated and dry masses via the use of a vacuum tube. Permeability measurements were calculated by putting the samples in a pressurized core holder and passing the fluid directly along it at constant flow so that we could achieve a pressure gradient that we then applied to Darcy's law. Grain size measurements were calculated for the sandstones and limestones using standard ASTM E11 specification standard testing sieves. And for the Nankai samples, due to the nature of the rock, we had to use precision hydrometer techniques in order to correlate the rate of sedimentation to the appropriate grain size distribution using Stokes' law of settling. These are the results we gathered from that. For the Boise, Berea, and Texas green, those are the 2 sandstones and the limestones, respectively, we were dealt with. It would appear that grain size and porosity are the major players, and that sorting is not as big a player, but that's a bit deceiving because the Boise sandstone had the highest permeability of all 3 of these, despite the fact that it had the porous sorting. And we believe that this is due to the fact that it had the greatest grain size and the highest porosity, thus offsetting the value of that. Also, the Berea sandstone had a much higher permeability than we were expecting, and we believe because it had a lower median grain size, lower porosity, lower sorting value, and we believe this is due to the fact that the nature of the limestone and the fact that fluid, as it's traveling through the rock, will naturally precipitate calcite along the pore throats, thus restricting the apparent permeability. For the Nankai sediments, we see that porosity does not have very much of an effect on overall permeability, and as far as we could tell, sorting had really none, which is why we didn't include this graph. And so median grain size seems to have the only decent influence on that permeability value. We included some graphs up here to give some sense of scale of the grain sizes. In this case, we used the Boise sample for the sandstone to represent the sandstones and limestone, and we have one of the Nankai samples. And we also included some mineralogy photos to give an example of the kind of mineral content of each of these rocks. And mineralogy did not, on the surface, appear to be all that significant, except in the case of the limestone, due to the precipitation of calcite around the pore throats. So overall, we determined that the permeability in rock is due to roughly 4 characteristics, that is sorting, connectivity, porosity, and median grain size. However, the influence of each of those depends on the lithology of the rock in question. In the case of clay stones such as the Nankai, median grain size is really the only significant factor, whereas in others, porosity and sorting have more significant influence. And that is my presentation. Thank you.